Welcome to developing and launching a new replication system. I'm Peter Engström. I work as a senior network programmer at Epic, and I'm celebrating 25 years in the industry this year. But more importantly, I'm one of the architects of Iris. So that's what we're going to talk about today. So a bit about the background, design and architecture, user-facing components, porting, Fortnite, debugging and optimization, and the future. That's the agenda for today. I could talk about this for hours, but I only have 50 minutes. So back in 2018, me and my co-architect Mattias Hörnlund joined Epic, having refactored the replication system in another game engine. And we pitched a data-oriented design approach to replication. At this time, Fortnite had become huge, still is, and replication graph had been developed to deal with the number of replicated actors and connections it required. But it was still struggling with high density action like in competitive games. Team Sweeney started talking about creating a metaverse, and we had quite a few developers on the team. So maybe 2 of them could invest a bit in the future. And Iris was born. So design and architecture. We had some key pillars when designing Iris. We wanted a clear separation between the game and replication system. And within the replication system, you have no access to objects. Of course, you needed to perform well, scale well with high object counts and connections. And also with the data-oriented design, it lends well to multi-threading and vectorization. It's important for us that it shouldn't be a massive undertaking for you to getting up and running in Iris. And obviously, we support property replication and RPCs out of the box. And lastly, a foundation for the future, because we have no actor or engine dependencies. We can replicate anything, as long as you can describe what you're trying to replicate. So what does it mean in practice? Yeah, on one side, we have the replication system. On the other side, we have game objects. But no access to objects in the replication system, you say. How do we do it? Well, we have the replication bridge, which you interact with when starting and stopping replication of an object. And when you start replicating an object, you'll get a netref handle back. And that you can use in the replication system API, which is a facade-style API forwarding calls to internal systems like filtering and prioritization. On the receiving end, we can create and destroy game objects as well. When it comes to marshalling the game data to the replication system, we have something we call replication states. And coupled with a replication fragment, which is an instance per game object, well, it's slightly more complicated, but we can think of it like that. We can use the property reflection to copy data to and from the source and target data, as well as perform relevant network callbacks like onReps. And the replication state has a memory buffer described by a replication state descriptor, which contains offsets, conditionals, traits, and how to serialize a member. And as you hear, there's an extra copy of the source state data so that we can detect which properties have been dirtied or updated. There's a lot that we can improve here. If the game object side had a typed property replication fragment, or typed replication fragment, we could, instead of performing onReps and use the property reflection with virtual function calls, we could call a native apply when we receive data, where you get all the state, and your can perform your game logic in arbitrary order and do native member compares if necessary. Looking how our net update looks, there are 5 main steps involved in the replication. It's filtering, poll and copy, quantization, prioritization, and serialization. And we'll look at how this looks in Timing Insights, a great tool. I hope you use it. We can see that we're performing all work at once for each of these steps. So the filtering produces a list of objects relevant to a connection. And when we know all connections requirements, we continue with the poll and copy phase, and we only need to check any objects that are relevant to any connection. The quantization is where we transform the source data into a plain old data format that is fast to serialize during the serialization phase. There you can perform expensive transformations like transforming F string to UTF-8, for example. This is only done once per object, so anything you do there, you don't have to do during serialization time. And prioritization is responsible for producing a list of which objects are more important to replicate. And finally, when we serialize everything, it will use that list, and we'll see what ends up in the packet. Usually there's too much that you want to replicate, so that's why we need a prioritization. So where do you come in? What do you implement in this pipeline? Filtering, of course. There are various reasons for doing it. Level streaming is a big one. If we can't instantiate the object on the receiving side, there's no point in sending it in the first place. And often you want to replicate something just to one or more, a few connections, like the player controller is only replicated to its own connection. And finally, as an optimization to save server and client performance and also client memory. And here's where you can do, for example, spatial filtering. So we have 2 different kinds of filtering. One is static, which cannot be overridden, and one is dynamic, implemented through net object filters, and that's typically where you come in. And if you filter out something in a net object filter, it can be overridden by inclusion groups. And this is a useful thing, for example, for spectator logic and things like that, when you want something replicated to an extra connection or something. Exclusion groups, you create a group through the replication system API, you add a few objects, and which connections are allowed or disallowed to have them replicated. And we cache any modifications you do each frame. So if you're not doing anything in frame, that saves time during the filtering phase. And owner filtering, that's the regular be only relevant to owner thing you find on the actor. But if you're not using actors, you can use this filter by code. So net object filters, it's called every frame for every object assigned to that filter. So it can be expensive. Usually, you want to try to implement things through exclusion and inclusion groups instead. And finally, inclusion groups, it's almost the same API in the replication system, but it can override the net object filter if the net object filter disallowed replication. Hence, inclusion group, it cannot do anything other than enabling replication of an object. to one or more connections. There's also dependent actors, which isn't filtering, but those can also override net object filters. And prioritization. We don't use the net update frequency to prioritize or throttle replication. Instead, we use prioritization. So the net update frequency, that controls how often we poll your object and check for dirty properties, whereas prioritization will dictate when something is replicated or not. So priorities are accumulated until the object is replicated, and then it's reset. And a priority of 1 means we're allowed to replicate it. So that's how you use it as a replication frequency throttling, by having a priority less than 1. And that's quite common, for example, for spatial prioritization. And you implement that through a net object prioritizer. Of course, we have a few useful ones in the engine already, but you can implement your own as well. And finally, serialization. That's slightly different from what you're used to. For example, we don't support NetSerialize on a struct. You have to implement, well, not have to, but often you need to implement a NetSerializer instead. And that deals with a particular property type or struct. But since we support all properties that is supported by any other replication system in the engine, you'll mostly deal with the structs. And as I mentioned before, it is responsible for transforming source data into a native network format that is plain old data format that is effective to serialize to bitstream. And you can also optionally implement delta compression. It's bit packing against the known baseline. You can save a lot of bandwidth depending on what kind of types you have, and we implement it for a lot of primitive types and quantized F vectors and such. And here's the only code slide I'll show today, the NetSerializer API. It may look a bit daunting. For a primitive type, it's not that much you would have to implement. Then it's just the type def of the source type and serialize and deserialize. But since you will be porting structs to this, you may need to implement a few more of these functions. Quantize, dequantize, that's transforming from the source state to the network format, is equal to determine if either two source instances are equal or two quantized instances are equal. Serialize delta, deserialize delta, that's for the delta compression and completely optional. Validate is something we don't call yet, but you should still implement it. We may start using it for RPCs to validate the parameters that they contain values that you expect. So, for example, if you receive an invalid enum value, we would say that validation failed, and we wouldn't call the RPC. Clone and free dynamic state, that is in the case if you have dynamic memory allocations in your pod data. Since we need to clone and free baselines, these are needed. And collect net references if you have object pointers and such. We need to be able to call onReps when they're finally resolvable on the receiving end. And apply is if you need a bit of a custom application from the dequantized data to the target instance. We always dequantize to a temporary instance. So if you don't want to overwrite something that is a replicated property, you may want to implement apply. So let's go over to porting and the lessons we learned while porting Fortnite to Iris. So we started the Iris development in 2019. And the first things I did was implement, after picking the name, of course, implementing a test framework so we could test everything, because we predicted having to switch replication systems live, and also rewrite or implement a new bit stream that was more efficient than the existing one. So me and Matthias, we worked for about a year in the cave, and it started to look promising. So we went and started trying to port Fortnite. And we struggled for 2 years. It was hard for just 2 people to catch up with all the Fortnite development. And there were also some major refactorings going on of systems that we had already fixed, and now we had to re-implement them. But after those 2 years, we felt, okay, it's not too buggy. Maybe we can seriously think about shipping it for real. And that's when we moved to UE5 main branch, released Iris as experimental in 5.1. We got some more devs to help out, and also QA. But it took almost 2 years, but we shipped Iris in Fortnite in April last year. We didn't announce it, we just switched the button. So, a lot of the work, well, not a lot of the work, some of the work was, as I mentioned, we don't support NetSerialize. You'll get a warning if we encounter a struct with NetSerialize that is used in replication, and then you can take a look if you need a custom serializer or not. In Iris, structs are replicated atomically, but they weren't previously. So one of the reasons to implement NetSerialize was to get that atomicity. So you just need to mark up your properties correctly. So in structs, that means mark properties as not replicated if they're not replicated, and have them as U properties if your NetSerialize method accesses a member. Conditionals is quite common. Rep movement is an example where whether you replicate physics or not, you replicate angular velocity or not. And to mimic that, you need to implement a NetSerializer. And there can be other bandwidth optimizations like custom quantization. We encountered cases where we actually had higher precision in the struct, but that led to gameplay bugs. So for bit perfect compatibility reasons, you may need to implement the NetSerializer in that case as well. But I mentioned we want you to get up and running as quickly as possible, so there is a quick hack you can use. The macro UINet implement named struct last resort NetSerializer and registry delegates. I hope that scares you off. Use it as a last resort, but of course for debug type structs you can leave it. But you're not getting any of the benefits of Iris, and we shoehorn your serialization into Iris. You won't see in the network insights or anything what you're actually replicating in there. So, but it's there. The Fortnite was using RepGraph, and we have some equivalents for the basic functionality. So you basically only have to tag which classes you'd use being relevant, never relevant, or use 2D spatial filter. Sometimes there was replication throttling going on, and as I mentioned, that's the job of the priority system. And so we implemented a few net object prioritizers that were useful for RepGraph, and all of those are in Iris or engine code. For always relevant for connection, you can make something not relevant using the ini-file configurable configuration and add an inclusion group. For groups and spectators, there can be a combination of dynamic filtering, inclusion groups, and perhaps exclusion groups. RepGraph also has a couple of features. I'm not sure how much they're used, but you can override cal distances and add dependent actors, and that's something we support through replication system util. Now, we encountered lots of bugs during the porting, and many of them were related to different types of ordering issues. And one is RPCs relying on replicated properties that were not updated for one or other reason. Even if you update the property and send an RPC in the same frame on the server side, it doesn't mean they end up in the same packet or will be received on the same frame on the client side. And if you have pointers to objects or anything else, they may require a sync loading or an actor to be replicated. So you never know when those are going to be updated, really. Another issue with properties is that you can't really rely on on-rep order for the similar reasons as RPC couldn't rely on properties. Sync loading and objects that haven't been replicated yet. And finally, actor dependencies don't rely on an actor being replicated before or after another actor. Even with add dependent actor, all you know is it will be replicated, basically. And there's also a combination of all of these three. One thing you can do prior to porting is run your game with packet simulation with high latency and high packet loss. Don't be shy of using 10-20% packet loss when testing. I'm sure you'll find a lot of bugs using those tools. So that's available in the engine. I think it's on by default in the editor, actually, but I may be wrong there. Use it in your playtests and when you're testing yourself. Some of the pain points, ordering issues, lots of pain. Structs with NetSerializers, well, we have had to go through each and every one of them. Since we have actually implemented a feature, for example, if you have a struct with a base struct and a bunch of inherited structs, you don't need to implement NetSerialize if you're only adding some replicated properties. And that's unlike NetSerialize, where you would have to make sure you call the parent NetSerialize. So you only need the NetSerializer where it's actually needed. Blueprint debugging, yeah, it wasn't fun because we basically didn't know the game and we didn't know how the blueprints worked, and it's generally just painful debugging those. And sometimes you would be required to load up the whole level and you didn't know which blueprint it was involved at all. Iteration times, we had lots of problem with that. Even if we had a green build, it didn't mean that we could find or test what we were looking for that particular day. With Fortnite, the level changes all the time, and a new release comes out every 2 weeks. And maybe we didn't have time to look at that until 2 months later, and then you couldn't look at it because it was gone, and we didn't know what we were looking for in the first place. And on the upside of things, we fixed a lot of bugs thanks to tools like the packet simulation. We went through pretty much every aspect of replication in the game. We could fix suboptimal things. We encountered some things that were impossible or very hard to implement. The no object access thing could sometimes be a hurdle, but could also spawn a new feature like the new lifetime condition dynamic, which allows you to change the lifetime condition of a property at runtime. And that works for iris and non-iris. Fixing things is a great way to learn, both us as network programmers learning how certain gameplay features work, but also at the end of the porting effort, when other developers started pitching in, they learned iris. So some of the lessons learned: work in the main development branch. We worked isolated for 4 years, and that was quite painful. And as I mentioned, the code changed a lot. So if you don't have your code alongside in the main branch, people can break your porting efforts. And you should also compile with your code enabled. We had a define everywhere to be able, not to impact the Fortnite executable size until it was ready to ship. That you don't need to do that. Get QA involved early, test with and without iris, and test with and without packet simulation, particularly with packet simulation. And collaborate with those who knows the features that are going to be ported. That will save a lot of time. So, some debugging tips and tricks. Network Insights is a great tool to inspect the packet contents. On the top view, you have the packet size and whether the packet was lost or not, which is a lost packet is indicated by a red bar. And on the bottom view, you have the bit-perfect packet contents. So make sure to use UINet trace macros when you implement NetSerializers, for example. For runtime debugging, we have a few functions you can call from the immediate watch window, for example, to print state and other things. Very handy. They're located in irisdebugging.h. And we also have some console commands to help you debug filtering issues and cull distance issues. They're located in object replication bridge debugging.cpp, despite what it says there. And some performance tips. While we strive to be as performant as possible, we're also running your code. But one of the tips is use push model on your properties. That would save a lot of time, particularly during the polling phase. You're probably going to use exclusion groups and other groups a lot, and strive to minimize your modifications to it. So sometimes it can be faster recreating a group rather than doing lots of modifications. And since we work on batches of objects, you can vectorize your code in NetObject prioritizers and filters. And use timing insights and CSV stats to track down perf problem. And then if you want to dig deeper, then use a sampling profiler. So what about the future? Well, Iris is still experimental and we want to go beta. So we will work on hardening the API. We haven't implemented support for seamless travel yet. We want to improve our unit test framework so you can write your own tests. And also implement replay, recording, and playback. That's currently using old school replication. So you need to keep both serialization variants up to date if you have replays. Thank you.